Okay, think about this for a second. Put $100 into a certain tech stock back in 1999. Today, it'd be worth, what, almost $500,000.
Wow.
Yeah. And even if you only invested, say, 5 years ago, that same $100, maybe 1,500 now.
Crazy growth.
Totally. And the company we're talking about is Nvidia. Now, you probably heard the name, right? Maybe in gaming?
Sure, yeah, graphics cards.
Exactly. But there's, like, so much more going on under the hood.
Oh, absolutely. What's really fascinating, I think, is just NVIDIA's journey, their whole trajectory. They started with this really specific goal, and somehow they've become this absolute cornerstone of the whole tech world.
Right. So in this deep dive, that's what we want to unpack, that incredible evolution. We'll look at the key tech, the people behind it, the rivals.
Yeah, and where they might be headed. We're drawing on this really great article that maps it all out.
Exactly. And the goal isn't just, rehashing stuff about graphics cards people already know.
Right.
We want to get at what's really driving modern AI, how NVIDIA got into that kind of crucial spot.
And maybe pull out some interesting business lessons, too.
Yeah. Get ready, because this is the story of how a company went from making PC games look prettier to, well, powering the biggest AI models out there.
And like the article says, it all started back in the early 90s. Very specific goal, developing market.
Okay, picture this. 1993. A Denny's in San Jose.
The classic Silicon Valley origin story location.
Right. Berryessa Road, East San Jose, apparently. And you've got 3 engineers, Jensen Huang, Chris Malachowski, Curtis Prime.
Okay.
Their backgrounds, Sun Microsystems, IBM, big tech places.
Just solid pedigrees.
And their big idea back then, basically, make PC games look as good, as immersive as console games using dedicated 3D hardware.
Yeah, which makes sense. There was a big gap back then, wasn't there, between console visuals and what PCs could do. And they saw that gap and aimed right for it with dedicated accelerator cards. That kind of focus. It's often key for startups, solving one specific problem really well.
Even the name's got a story. They had this internal code name, NV, like next version. And somehow that morphed into NVIDIA Latin for envy.
Envy, okay.
Then they just dropped the I.
NVIDIA.
Kind of memorable, right?
Definitely signals ambition from day one. But it wasn't all smooth sailing at the start. The article really flags their first product, the NV1 in '95, as a tough lesson.
Oh, absolutely. The NV1, it was supposed to be this, like, wonder card, right? 2D, 3D graphics, sound, even Sega gamepad ports.
Yeah.
All on one board.
Super ambitious. Maybe too ambitious.
Seems like it.
Yeah.
The killer problem. It used quadratic textures.
Ah.
Meanwhile, Microsoft's DirectX, which pretty much took over, that was all about triangles. Developers just didn't bite.
And the fallout was pretty bad, right?
Yeah.
Diamond Multimedia, their main customer.
Returned like 250,000 units. Yeah. The article says NVIDIA came really close to going bankrupt right then.
Wow. That just hammers home that lesson, doesn't it? You have to work with the standards, with the ecosystem. If developers aren't using your stuff.
Doesn't matter how cool the hardware is.
Yeah.
You're dead in the water.
Talk about a trial by fire. So the big lesson, like the article says, work with the developer ecosystem. Don't fight it.
Exactly. Which brings us to the turning point, 1999, the GeForce 256.
Right. This was huge, not just for NVIDIA, but kind of for all of PC gaming.
Definitely. And this was the first time they really pushed the term GPU, right? Graphics Processing Unit. I think the article credits Dan Vivoli for that.
Yeah, coining and promoting it. And it wasn't just a name change. It was a fundamental shift in how graphics worked.
Explain that a bit. What was the big deal?
Well, basically, it took all the heavy lifting for 3D geometry and lighting off the main computer chip, the CPU, and put it onto this dedicated graphics card, the GTU.
So the CPU was freed up and the GPU just crunched the graphics numbers. Exactly. Games got way faster, looked way better. It was like revolutionary at the time.
Total game changer. And that momentum probably helped with their IPO in January '99.
Must have. Yeah. $12 a share.
Yeah.
Gave them the cash they needed. But their growth strategy after that was also super important. This whole ship fast, ship often thing the article mentions.
Right. That rapid iteration. That became a massive advantage for them.
Totally. They were cranking out new stuff every 6 months or so.
Yeah. When the rest of the industry was more like, 18 months?
Exactly. Just relentless innovation. They grabbed key design wins. They powered the original Xbox.
Oh, yeah. Forgot about the Xbox connection.
And by 2005, they were pretty much the dominant player. The consumer graphics, professional graphics, the works.
So that whole early phase, it really comes down to learn from your mistakes. Like, really learn.
Mm-hmm.
Embrace the ecosystem, don't fight it, and just out-innovate everyone with speed. Built a really strong foundation.
Absolutely. But yeah, the story definitely doesn't stop at just being the kings of gaming graphics. Around the mid-2000s, they started looking, well, beyond just graphics.
Yeah, this is where it gets really interesting, the pivot towards parallel computing.
Right. Two big moves there, the article highlights.
Yeah, CDA in 2006 and then the first Tesla cards in 2007. These were really strategic plays to use that GPU power for way more than just pretty pictures.
Okay, let's break down CDA first. Compute Unified Device Architecture.
Sounds fancy.
It kind of was. It was basically software that let programmers using standard C++ NE tap into the, thousands of cores on an Nvidia GPU.
So using the graphics card like a general-purpose math engine.
Pretty much, like a coprocessor.
Yeah.
But as the article notes, it wasn't an instant hit.
No, why not?
Well, bit of a learning curve for coders, apparently, and maybe the immediate need wasn't obvious. People felt their CPUs were okay.
Yeah, that happens with disruptive tech sometimes. Takes a while for people to catch on, figure out the killer apps. And the Tesla cards in '07.
Right, these were basically GPUs, but with no video ports. Just pure compute power.
Aimed at workstations, high-performance computing clusters.
Yeah, they called them pocket-sized supercomputers. But again, the reaction was kind of lukewarm at first.
Okay, so not an overnight success then.
Definitely not. But Nvidia stuck with it. They kept polishing CUDA, making it easier to use, adding helper libraries.
At distance.
And then, around 2008, 2009, things started clicking. The article mentions researchers showing, chemistry simulations that took a week on normal computers. Could be done overnight with CUDA GPUs.
Wow, okay. That's a big difference.
Huge. And banks found their risk models ran, 50 times faster.
50 times. Okay, now you're talking real business value.
Exactly. So suddenly, universities, hedge funds, they started buying those Tesla cards.
Yeah.
Seeing those actual speed-ups, that was key.
Right, demonstrating the concrete benefits. That overcomes a lot of skepticism. And then came Fermi in 2010. Another big step.
Yeah, this was huge for reliability, especially for the serious scientific computing crowd.
How so?
The Fermi architecture added stuff like error-correcting memory, ECC memory, and much better math for double precision calculations.
The kind of accuracy you absolutely need for complex simulations, building trust with the supercomputer folks.
Precisely. And the proof was in the pudding, or rather, the TOP 500 list.
The list of the world's fastest supercomputers.
Yep. By 2011, machines using Nvidia GPUs were cracking that list. The article says 3 of the top 5 supercomputers then were using Nvidia Tesla GPUs.
Okay, so that's mainstream acceptance right there. GPUs weren't just for games or niche science anymore. They were for serious compute, finance, science, and AI.
Exactly. That period, maybe 2006 to 2011, that's Nvidia making the jump. From just graphics to this high-performance computing powerhouse, it took time, persistence, building the software.
But it totally paid off, and it perfectly set the stage for their eventual dominance in AI.
Which really kicked into high gear around 2012, right, Alex?
Oh yeah, AlexNet. That was the watershed moment. Absolutely pivotal.
So a team at the University of Toronto, they trained this AI model, AlexNet.
For image recognition, yeah. The ImageNet competition.
Right, and they did it using a couple of off-the-shelf NVIDIA gaming GPUs.
Not even the fancy Tesla cards.
Nope. And they just blew the competition away.
Yeah.
Suddenly, the whole AI research world kind of woke up and went, whoa.
These gaming chips, they're actually amazing at the math AI needs.
Exactly. It turned out that the parallel structure, great for graphics, was also perfect for the matrix math in neural networks.
Which is fascinating, right?
Yeah.
The hardware wasn't designed for AI initially, but it was just incredibly well suited.
Totally. And that realization caused this massive shift. Labs started ditching their old CPU clusters.
And buying up Nvidia cards, and then VC money, big tech money. It all started pouring into deep learning, pretty much all running on Nvidia gear.
But Nvidia wasn't just looking at the giant data centers. 2014, they bring out the Jetson TK1.
Right. AI at the edge. This was important.
What was the Jetson TK1?
It was this small, kind of low-power board, but it still had CUDA and their TensorRT software for running AI models efficiently.
So you could suddenly put an AI brain into, robots, drones, factory cameras.
Exactly. Student projects, even. Made AI much more accessible, physically smaller, less power-hungry, and they kept iterating TX1, TX2, Xavier, Orin.
More power, same small sum.
Yeah, and they bundled it with the Jetpack, Software Kit CUD, cuDNN for deep learning, TensorTAC, even robotic stuff like ROS support made it easier for developers to actually use it.
So democratizing AI power beyond just the cloud giants. And then 2016, they make another big move,
Huh.
the GGX-1.
The AI supercomputer in a box.
Pretty much a ready-to-go plug-and-train system.
Yeah, instead of researchers spending ages building and tweaking their own AI servers.
You just unbox this thing, plug it in, start training models. It had, what, 8 top GPUs, all the drivers, libraries preloaded.
Exactly. Lowered the barrier significantly. And that concept just scaled up DGX A100, H100, now even DGX Cloud, where you can rent the power.
So they shifted from just selling chips to selling, like, complete AI factories.
It's a really smart evolution of the business model.
So, okay, 2012 to 2017, that's Nvidia cementing itself as the platform for AI. From tiny edge devices with Jetson to massive training clusters with DGX.
Absolutely. Which brings us pretty much up to the present day, what the article calls the AI backbone.
Good name for it. Because, I mean, today, pretty much all the big AI models you hear about, OpenAI, Microsoft, Amazon, Meta, Tesla.
They're all built on Nvidia hardware. Overwhelmingly, that core GPU tech born for gaming is now the engine of the AI revolution. It's kind of wild.
The article mentions some key recent chip architectures, Turing in 2018.
Yeah, Turing was significant. It introduced Tensor Cores hardware specifically for AI math alongside the RT cores for ray tracing and graphics.
So the graphics chips themselves started thinking more efficiently about AI tasks.
Exactly. Then Ampere A100 in 2020. That was a piece.
What was special about Ampere?
It could be split into smaller, independent mini GPUs, so one card could handle multiple AI jobs at once. Super useful for cloud providers. That powered a lot of the GPT-3 training.
Okay, and after Ampere, Hopper H100 in 2022?
Right. Hopper brought things like the FP8 data format and the transformer engine, which gave a big speed boost for training large language models specifically.
And most recently, the H200 in 2024.
Yeah, the H200 is basically the H100 silicon, but with a lot more super fast memory. Really key for serving those huge AI models efficiently once they're trained.
And looking just ahead, Blackwell, B200, GB200, sounds like another big leap.
Huge leap promised, yeah. Faster speeds, new system designs, even liquid cooling. It's just constant rapid-fire innovation.
And like we touched on with DGX and DGX Cloud, it's not just about the chips anymore. It's the whole solution.
Totally. The DGX systems are these pre-built AI supercomputers, top GPUs, super fast NVLink connections between them.
NVLink, remind me what that is.
Oh, right. NVLink is NVIDIA's own high-speed interconnect. Lets their GPUs talk to each other really, really fast within a server, much faster than standard connections, essential for massive AI training.
Gotcha. So DGX has the GPUs, NVLink, fast storage, all the software ready to go.
Yep. And DGX Cloud just makes that rentable through AWS, Azure, Oracle.
Yeah.
Pay by the hour or month. Makes it accessible.
And they've also been tackling the data bottleneck problem, right?
Yeah.
Moving data around fast enough. The Mellanox acquisition in 2020 was key there.
Absolutely crucial. Mellanox were leaders in high-speed networking, InfiniBand, fast Ethernet. You need that to connect thousands of GPUs without things grinding to a halt.
Makes sense.
And their newer stuff like Spectrum-X switches and Bluefield DPUs, those are designed to optimize traffic within these AI clusters even more.
DPUs, data processing units.
Yeah, Bluefield DPUs are basically smart network cards. They can handle networking tasks, storage tasks, security tasks. Taking the load off the main CPUs and GPUs makes the whole system more efficient.
Smart. And they're even making their own CPUs now, the Grace CPU.
Yep. An ARM-based CPU, and they pair it with a GPU in the Grace Hopper superchip. The idea there is to get data into the GPU incredibly fast, like 900 gigabytes per second, again, tackling bottlenecks.
Wow. Okay. And beyond the data center, the tech keeps spreading. Cars, robots.
Definitely. Drive Thor, based on Blackwell tech, is aimed at cars running the dashboard, entertainment, self-driving features, all of it. And Jetson just keeps powering more edge devices, robots, factory cameras, smart city stuff, all using that same CUDA and Tensor 8 software base.
So it's this whole accelerated computing focus, as the article says. Data center AI is the big moneymaker now.
Yeah, like 90% of revenue.
But the software, the networking that locks customers in, and then edge, auto, pro graphics, gaming.
Yeah.
It all expands the reach.
Exactly. It's a full stack approach. And their roadmap looks like yearly upgrades after Blackwell, Rubin Ultra, even talking optical wiring eventually, all aimed at faster AI, bigger models.
Just relentless. It really shows that long-term vision. But none of this happens without the right people, right?
Oh, for sure. The leadership has been critical.
Obviously, got to start with Jensen Huang. Co-founder, CEO since day one. He's the face, the strategist. His GTC keynotes are huge events.
Absolutely. The driving force. Then Chris Malachowski, another co-founder, now Nvidia fellow, more behind the scenes, shaping culture, long-term tech strategy.
And Ian Buck.
Yeah.
He runs accelerated computing now, but he actually led the original CUDA development back when he's a grad student.
Wow, okay. Talk about seeing your project through. And Bill Daly, the chief scientist. He leads NVIDIA research, things like tensor cores, FP8 math. A lot of that comes from his group.
Michael Kagan, too. Came over with Mellanox, now CTO. He's the interconnect guy, NVLink, Spectrum Networking.
Building the high-speed plumbing?
Crucial. And Colette Kress, the CFO. Managing the money for all that massive R&D, big acquisitions like Mellanox, that's a huge job, too.
Definitely a strong team. But, even with that leadership and tech lead, they're not alone. There are definitely companies trying to grab a piece of that AI pie.
Oh, yeah. Let's talk rivals. The article lays out the main contenders. AMD's a big one, right? Going for price performance.
Yeah, their Instinct MI300X accelerator, it actually has more memory and more memory bandwidth than NVIDIA's H100.
Really? Better specs in some ways?
On paper, yeah. And benchmarks show it can often match or even beat the H100 on some AI tasks, especially transformer models. Plus, it tends to be cheaper.
So why isn't everyone switching?
Software. AMD's ROCm platform, it's getting better, but it's just not as mature or widely adopted as CUD. That's NVIDIA's huge advantage to the ecosystem. But AMD is getting traction. Azure and Oracle are using their chips.
Okay, then there's Huawei. That's more of a geopolitical situation, isn't it?
Exactly. With the U.S. restricting high-end NVIDIA chip sales to China, Huawei's Ascend 910C is the main domestic alternative.
How does it stack up?
Per chip, it's maybe like 60% as fast as an H100, but they're scaling it up in big clusters. Alibaba, Baidu, Tencent, they're all using it.
But same software issue.
Yep. Their Canison software is playing catch-up to CUD. Takes more effort to develop for.
Intel's in the game, too, with Gaudi 3, positioning as a bargain.
Yeah, they're claiming better performance per dollar, especially for AI inference compared to the H100. Gaudi 3 is supposed to be widely available later this year, 2025.
But again,
the software tools, the developer community, it lags CUDA significantly. That's the big hurdle for both AMD and Intel.
And maybe the biggest long-term threat. NVIDIA's own customers building their own chips.
That's definitely one to watch. Google with their TPUs, tensor processing units, AWS with Trainium for training, Inferentia for inference.
Why are they doing that?
Control, optimization for their specific needs, and yeah, probably cost. Reducing reliance on NVIDIA could save them a lot of money and potentially squeeze NVIDIA's margins down the road.
So Google uses TPUs mostly in-house, but you can rent them on their cloud.
Exactly. It signals that the biggest buyers are looking for alternatives or at least ways to diversify.
So NVIDIA's defense is basically keep CDA awesome and ship Blackwell really, really fast.
Pretty much. Maintain that software moat and keep pushing the hardware performance edge. It's a tough balancing act.
Okay, let's shift to the money side, because the numbers here are just staggering. The article calls it NVIDIA's money machine.
And that's not an exaggeration. That shift into being the core AI hardware provider, it's turned them into an unbelievable cash generator. It's mostly data center revenue now.
The figures are wild. Market cap briefly hit $3.3 trillion earlier this year, second only to Apple.
Yeah, insane valuation. Fiscal year 2025 revenue, $130.5 billion. That's up 114% year over year.
And profit.
Net profit, $72.9 billion, up 145%. They're throwing off something like $40 billion a year in operating cash flow.
Wow, which pays for all that R&D and buying companies like Mellanox.
Exactly. And yeah, around 90% of that revenue, data center products and services. Geographically, it's roughly half U.S., half Asia.
Just incredible financial performance, all driven by this AI boom. So looking forward, the article weighs the good and the bad. Let's start with the sunny side. Why does the future still look bright for NVIDIA?
Well, number one, the AI race isn't slowing down. If anything, it's accelerating. More companies, bigger models. That just means more demand for compute power, which NVIDIA sells.
Okay, demand stays strong. What else?
Their own innovation continues. We talked about Blackwell, Rubin coming in 2026. They keep pushing the performance envelope.
Right. Plus, their business model is getting smarter, more diverse.
Exactly. DGX cloud subscriptions, the Grace Hopper chips selling CPU and GPU, the high-speed networking from Mellanox, the software like CUDA and AI Enterprise, it all creates stickiness, lock-in.
And they're pushing into new markets, too. Cars with Drive Thor, robotics with Jetson.
Yeah, those are potentially huge future growth areas. Diversifies them beyond just the data center cycle.
Okay, so lots of reasons for optimism. But what could trip them up? What are the potential headwinds the article mentions?
Well, export controls are a big one. China was, what, 17% of revenue in FY25? If those restrictions tighten further, that could definitely hurt.
Makes sense.
What else? The idea of good enough AI, like that DeepSeek model trained relatively cheaply, if really effective AI can run well on less expensive hardware.
That could undercut demand for Nvidia's top-tier pricey chips.
Potentially, yeah. And then there's the competition. We talked about AMD, Intel, the cloud providers on silicon. They're hungry.
Any supply chain risks?
The article specifically calls out HBM high bandwidth memory. Crucial component, only a few suppliers. Any shortages or disruptions there could directly impact NVIDIA's production.
Okay. And finally, just the sky-high valuation itself.
Yeah, when your stock price is that high, you're priced for perfection. Any stumble in earnings miss, a delay, bad macro news could hit the stock hard.
So, yeah, strong position, huge demand, but definitely operating in a complex world. Geopolitics, competition, supply chains, lots of moving parts.
Absolutely.
This has been really fascinating, kind of tracing that whole arc. So let's try to boil it down. What are the key takeaways from this whole NVIDIA story? The article suggests 5.
Okay, first one. Pivot fast, but persist hard. Think NV1 failure to GeForce success. Or how CDA started slow, but they stuck with it until it dominated.
Right. Resilience and adaptability.
Second, have a clear long-term vision. For NVIDIA, it's been accelerate everything. CPU plus GPU, data center, edge. It's all about making computing faster.
Third takeaway. They really are the AI infrastructure backbone now. If you're doing serious AI, odds are you're using NVIDIA tech somewhere.
Fourth, they've built this full-stack moat. Hardware, software, networking, it's all integrated. Makes it really hard for customers to just rip and replace them.
Creates that lock-in we talked about.
Yeah.
And the 5th key takeaway.
Their lead is huge right now, but the threats are real. Export bans, those hungry rivals, potential HBM shortages, maybe good enough AI alternatives. Like, they can't rest on their laurels.
Definitely not. So for anyone listening who wants to dive even deeper, the article had some good suggestions.
Yeah, a few things. There's an upcoming book, The Thinking Machine by Stephen Witt, specifically about Jensen Huang and NVIDIA. Also, Chip War by Chris Miller for the broader semiconductor context.
Good recommendations. Podcasts.
The Acquired podcast did a really deep 3-part series on NVIDIA's history. And of course, watching NVIDIA's own GTC keynote presentations gives you the latest directly from them.
Great resources. Okay, so wrapping this up, it's just an incredible journey, isn't it? From PC gaming graphics cards to literally being the engine driving the AI revolution. We've hit the key moments, the big decisions, the people involved.
Yeah, they're in this massively dominant position right now. But like we said, it's a dynamic field, lots of competition, lots of challenges ahead.
Absolutely. And maybe here's a final thought to leave you with. Given NVIDIA's central, almost indispensable role now in developing and deploying AI, what does that mean for us? What are the bigger societal implications, the ethical questions as their technology gets woven even deeper into everything we do? Something to think about, the future being built on this powerful engine of AI.